Welcome to the third day of the workshop, and it's my great pleasure to introduce our first speaker, Alexei Poltoratski from University of Wisconsin-Madison, who will continue his mini course, and today's lecture will be devoted to pointwise convergence for the scattering data and nonlinear Fourier transform. Alex, please.
Thank you very much. So today we'll finally get to the problem of, excuse me, extending the classical Carlson theorem on pointwise convergence of Fourier series to the nonlinear settings. And this is just one of many problems that exist in this area, which we've been talking about for the last two lectures. The area is the includes spectral problems for differential equations, along with scattering problems, and many questions like this one appear along the way. So let me start by reminding you the history of the original problem, which is, of course, related to the classical linear Fourier transform. And this is the definition of the Fourier transform of a function, which, as you remember, is initially defined for L1 functions on the real line. And then we notice the Parseval identity and extended to L2 functions. And let's quickly recall these three basic properties of the linear Fourier transform. Of course, that's not a full list of even basic properties, but I'm listing these three because it will be easy to see the same properties in the nonlinear version of the Fourier transform that we will define later. So number one property is that if you modulate the function, then the Fourier transform gets shifted. The second property is that if you rescale the function, then the Fourier transform gets rescaled in the opposite direction. And finally, Parseval's identity, which says that the Fourier transform preserves the norms. And so now let's recall that famous problem, which was first, of course, formulated in the 19th century for Fourier series. But here is a slightly more modern reformulation. So instead of partial sums of the series, let's consider partial Fourier integrals from minus t to t. And then let's tend t to infinity and ask if these partial sums or partial integrals tend to the full Fourier transform of f at almost every x. And of course, most of you know the history of this problem, but let me just remind you some of it because it's really a fascinating story which contains so many famous names. The question about the convergence of partial sums of Fourier series was formulated by Fourier himself in the 19th century. Of course, terms like almost everywhere did not exist back then, so it was formulated for continuous functions and all x. It was proved for smooth functions by Dirac in 1829, and then disproved for continuous functions by Dubois-Reymond in 1876. Then with a slightly weaker convergence, it was proved by Fourier for Cesare means. And then finally, the time of modern analysis began, and the Lebesgue theory became the mainstream of analysis. And in its modern form, the question was formulated by Luzin in 1915 for L2 functions and almost every x. It was shown shortly by Kolmogorov that the conjecture is false for L1 functions in 1923. And then further contributions to this problem throughout its history were made by many famous mathematicians, including Riemann, Weierstrass, Littlewood and Paley, Hardy, Zygmunt, and of course I'm only listing a small part of the famous names who contributed to this problem. And then, as you may remember, in 1966, Carlson solved this problem, proving that the integrals converge for almost every x and every L2 function. Then Hunt extended the result to other p's. And at present, we have alternative proofs of the same theorem by Pfefferman and by Lacey and Thiele. So in the next few slides, we will try to define the nonlinear version of the Fourier transform, which plays the same role as the Fourier transform, but in the theory of nonlinear differential equations. And then we will try to see the analog of this problem and prove a similar theorem. All right, and to define the nonlinear Fourier transform, we will go back to self-adjoint systems of differential equations, which we discussed in the first two talks of this mini course. So our main object in those two talks was the so-called canonical system, which doesn't have this part. What is written here is the so-called Dirac system. Now, a Dirac system is also a 2x2 self-adjoint system, which can be reduced to the canonical form with a substitution. So I'll remind you the general canonical form, which we once again have discussed in more detail in the first 2 hours of this mini course, but this Dirac system is a partial case of a particular case of a canonical system. And so in this equation, omega is like before a symplectic matrix like this, a root of -1 in the space of matrices. X is the unknown two-dimensional vector function. Q is the given function, and we will consider the so-called real Dirac systems where this function Q has this form. In a slightly more general situation, you would also have G and minus G on the main diagonal, because the trace should be 0 for this matrix Q in the Dirac system, and then the function f plus ig is called the potential of the system. Now, for simplicity here, we are considering the situation when G is 0, and so the potential is just f, and it's a real function. So we are considering a real Dirac system. As usual, f is assumed to be locally summable. We consider our equation on the half line from 0 to infinity. And as I already mentioned, any such Dirac system can be reduced to the canonical form with the substitution. The canonical form, as we discussed yesterday and the day before, is a very general class of second-order differential equations. Most known second-order equations can be reduced to this form, and it includes the Dirac system. I don't have enough time today to show you the substitution that needs to be made, but it's not very difficult. So every Dirac system is a canonical system. You may ask, how about in the opposite direction? Well, any canonical system can be rewritten as a Dirac system, but only if you allow distributions in Q. So not quite. If you rewrite a Dirac system as a canonical system, then all the entries of H will still be functions. But since the Dirac system is a particular case of a canonical system, this whole Crane-de branch theory with the branch entire functions and the branch spaces applies to Dirac systems as well. And let's recall that part of the theory as it applies to Dirac systems. So to study the nonlinear Fourier transform in the second part of the talk, we will need to consider the situation when this real potential F belongs to L2 on the half-line. And once again, let's solve the system, but look not for a two-dimensional vector function X, but for a matrix M with the initial condition I. So this is like putting the Dirichlet and Neumann solutions to our system as columns into one matrix. And once again, this matrix is called the transfer matrix for the system, or sometimes the matrician. And let's recall what is the scattering matrix for the system. We gave this definition yesterday for the canonical system. Here, let's give it directly for the Dirac system. So to find the scattering matrix of this Dirac system, you need to find the same transfer matrix for the free version of the system when Q is identically 0. So that becomes a very simple equation, and you can solve it. And this M0 matrix will be a rotation matrix consisting of sines and cosines. And then you do the following. You take the transfer matrix for your given system and apply M0 inverse, the inverse for the free transfer matrix. And then you try to tend T to infinity, hoping that the limiting matrix will exist in some sense. Now, some information about this limit was given in Sergei Denisov's talk the day before yesterday. So in particular, for each fixed finite T, the entries of all these three matrices will be entire functions in the complex plane. And when T tends to infinity, we will have some normal convergence for the entries. Just one second. For the entries of our matrices, some will converge normally in the upper half plane and some will converge normally in the lower half plane. And so, but for each entry of the matrix, there will be some kind of convergence. And so in some sense, at least under this restriction that the potential is in L2, you will always obtain this limit scattering matrix. All right, and on this slide, my goal is to connect the two equivalent notations. So we are dealing with this scattering matrix S coming from the Dirac system. And if you ever read, for instance, lectures on the nonlinear Fourier transform by Tao and Thiele from 2003, you may remember that the nonlinear Fourier transform was defined slightly differently. So in those lectures, the nonlinear Fourier transform was a matrix of this form with some functions a and b, and a sharp and b sharp is once again, like in our previous two lectures, is the Schwarz reflection of the function with respect to the real line. So here I'm trying to connect the two notations. And so let's take that scattering matrix for the Dirac system and make a change of basis in this matrix. Now, these two constant matrices on each side are inverse to each other. If you spread this coefficient 1/2 as 1 over root of 2 in front each of them, then there will be a change of basis matrix. Now, after this change of basis, we will obtain the matrix of this form, where A, B are entire functions and B sharp, A sharp are the reflections of those two functions. And this new function n will satisfy its own differential equation. And here is the differential equation for n. F is still that potential from our original Dirac system, which we assume to be in L2 on the half-line. So if we solve this differential equation with the initial condition I, and then try to tend t to infinity, we will obtain this limit functions. Since the limit of the scattering matrix exists and n is just a change of basis for the scattering matrix, this limit matrix will also exist. Now, for each finite t, the functions a, b, a sharp, b sharp were entire. But as you take the limit, you'll have convergence in half planes, but not in both half planes. So in the limit situation, when f is from L2, it's well known that b will end up being analytic in the upper half plane, and I will be analytic in the lower half plane. And on the real line, we will have this identity because the determinant of the matrix must remain equal to 1. On the real line, A sharp is complex conjugate to A, and B sharp is complex conjugate to B. So we get this identity because the determinant is 1. Now, so this matrix is called the nonlinear Fourier transform of F. F was the potential function in our original Dirac system, or the function from our second differential equation for n. And this is, by the way, the equation that you can find in many papers about the nonlinear Fourier transform. So if you look at this matrix n, this limit matrix when t tends to infinity, so once again, A is analytic and actually outer in the lower half plane, and B is analytic in the upper half plane, and their absolute values are related like this, then you can see that the absolute value of B is actually less than the absolute value of A. And so you can make a bounded analytic function in the upper half plane from A and B by considering B divided by A sharp. Notice that for this new analytic function in the upper half plane, B divided by A sharp, you can recover the whole matrix n from this one function. Because if you know the absolute value of this one function, and you know that the absolute values of A and B are related to each other like this, you can recover the absolute value of A and the absolute value of B. Now, A is outer, so its absolute value determines A completely. So after you find A, and you know B over A, you find B, and then you fill in the whole matrix N. So really, you don't need to look at the whole matrix. You can call this one bounded analytic function the nonlinear Fourier transform of F. And so once again, in the lecture notes by Tao and Thiele and their papers with Moscalu, the matrix is called the nonlinear Fourier transform, but you can also call this one function the nonlinear Fourier transform of F. So this is a more or less standard notation. I've seen it in several papers for the nonlinear Fourier transform. And this other version that we will consider in this talk, I'll use a slightly different notation. But the main thing here is that for the linear Fourier transform, the hat is linear, and for the nonlinear Fourier transform, the hat should be nonlinear like this or this. All right, so as I said, now we will concentrate on the second version, where the result is one analytic function, which, however, can give you the whole matrix if you prefer that notation. So let's look at the properties, and here we are trying to show that this new transform has a right to be called the nonlinear Fourier transform because it shares many properties with the linear Fourier transform. First of all, if you modulate the function, then its nonlinear Fourier transform gets shifted. If you rescale the function, then the nonlinear Fourier transform gets rescaled in the opposite direction, just like the linear one. Now, the Parseval identity in the nonlinear form, we do have an equation for the norms. It looks a bit more complicated than in the linear case. And some people may object that in the classical Parseval's identity, you have a Hilbert space equation of two L2 norms. And to that end, in many papers, they write the square root here and the L2 norm squared here. And this way, it looks more like the Parseval identity. Finally, the linear Fourier transform is the main term of this nonlinear Fourier transform in the following sense. If you multiply f by epsilon and then take the nonlinear Fourier transform and then tend epsilon to 0, then the main term here will be epsilon f hat, where f hat is the linear Fourier transform, and everything else will be much smaller. So the linear Fourier transform is a linearization of this new nonlinear transform. And finally, if you adopt this version that we are considering now, where you obtain a function analytic in the half plane, this is also the property shared with the linear Fourier transform, where the transform of a function on a half line was a function analytic in a half plane. All right, so this is, of course, not my idea to call it the nonlinear Fourier transform. Such view was adopted about 100 years ago, and many people noticed that this is a nonlinear analog of the Fourier transform. And if you look at the lectures by Tao and Thiele, there are even some examples on how to use it to solve nonlinear differential equations, such that a KdV equation, for instance. Of course, there is immediately a whole list of natural questions about this transform. Namely, we would like to find analogs of all the main theorems about the classical linear transform in the nonlinear settings. So, for instance, let's look at the Hausdorff-Young inequality, which relates the LP norms of a function and its Fourier transform. And indeed, here, at least for p between 1 and 2, strictly less than 2, we have this inequality, and this comes from the series of papers by Christ and Kiselov. Now, for a p equal to 2, we have the equation with the constant equal to 1, because that's the nonlinear version of Parseval's identity from the previous slide. But even here, it's an open problem to show that Cp, when p tends to 2 from below, tends to 1, because the existing constants that we have so far, they tend to infinity as p tends to 2. So 2 is a critical case, and it's the most difficult case in this in these settings. So as I was told, by the way, that this very famous series of papers by Christ and Kiselov was motivated initially by trying to solve the problem that we are discussing, to prove the almost everywhere convergence for the case p equal to 2. And unfortunately, their methods didn't give that result, although they ended up with many useful maximal estimates and this version of Hausdorff-Young inequality for p less than 2. And I should also mention here that they did everything in the settings of the Schrödinger operator, not the Dirac system, but these are two equivalent settings. So we can mention the results here as well. You can look at the paper by Moskalu, Tao, and Thiele for questions on maximal operators and other questions, and there are some other papers that also discuss open problems. But let's move on. And so now we will formulate the problem, and of course it's not difficult to formulate. So we'll restrict our potential function f, which is defined from 0 to infinity on the interval from 0 to t, calculate the nonlinear Fourier transform, that function b divided by a sharp, for ft, and then tend t to infinity, and ask if these partial Fourier transforms converge to the full Fourier transform at almost every x. So this question has been studied also in the paper by Moskalu, Tao, and Thiele in 2003. This was proved in a discrete model, in the so-called d-adic model. And at least in spirit, this result reminds you of the Fourier result in the history of the classical Fourier transform. But our goal is to prove this full analog of Carlesson's theorem. Let me tell you right away that in the classical Carlesson's theorem, the convergence follows from the maximal estimate. Now, it's not the same in the nonlinear settings. So they are still related. The maximal result would still imply the convergence, but the methods that I use to prove the convergence do not immediately give the estimates for the maximal operator. And this is still a work in progress. And today I'm not going to make any claims about the estimates of the maximal operator. So, but as far as pointwise convergence, we do have it, and here's the theorem. So if the potential is from L2, then partial sums, so to speak, converge to f hat at almost every x. So as I already told you, it seems that some estimates for the maximal operator could be extracted from the proof, but mostly because the examples of nonlinear Fourier transforms are so difficult to construct, it's not clear to me yet if those estimates are optimal. And so once again, I'm not ready to talk about the maximal operators. So the almost everywhere convergence result implies the boundedness of eigenfunctions for the Dirac system with L2 potentials, which was also an open question until now. The proof of this theorem is completely independent from the proof of the linear, from the existing proofs of the linear correlations theorem, and it relies on analyzing so-called resonances for the Dirac system. So once again, let's go back to the Dirac system. So in this part of the talk, I would like to show you some of the ideas of the proof. Unfortunately, I will not be able to go into technical details, but hopefully at least the flavor of the proof, well, I could relate to you here. So let's once more look at the Dirac system, and let's consider its solution X for some fixed self-adjoint boundary condition at the origin. And then, as we've discussed for a general canonical system, it's still true here, we can make an entire function out of the solution for each fixed t. And the function is defined like this. And it will always be an entire function of the Hermite-Biehler class, whose absolute values, this should be an absolute value, are bigger in the upper half plane than at the symmetric points in the lower half plane. And so if we solve the system with Neumann and Dirichlet boundary conditions, obtain two solutions, then from each of them we can make a family of Hermite-Biehler functions. And I'll denote those functions by E of Tz and E tilde of Tz. So for each fixed t from 0 to infinity, this is each of them is an entire function of the Hermite-Biehler class. I also need to remind you what is a meromorphic inner function. So an inner function in general, an inner function in the upper half plane is a bounded analytic function whose boundary values on the real line are unimodular almost everywhere on the line. Now, a meromorphic inner function is an inner function in the upper half plane, which can be extended meromorphically to the whole plane. Now, if you write the general factorization for an inner function and think about this condition of meromorphic extension, you quickly see that a meromorphic inner function has this form. As a singular factor, it may only have an exponential factor. And as a Blaschke product, it may only have a product whose zeros tend to infinity. There should not be any finite accumulation points. And of course, the zeros still have to satisfy the Blaschke condition. So if we go back to our Dirac system, which we used to define the nonlinear Fourier transform, solve it once again with this Neumann Dirichlet boundary condition. We can also make a family of inner functions out of this solution by this simple formula. And it turns out that sometimes it's more convenient to look at Hermite-Biehler functions E and E tilde, which we also defined using the solution. And sometimes it's more convenient to look at the inner version of those functions, this function. So for every fixed t, this function will be a meromorphic inner function. And we will call this whole family of inner functions the Dirac inner functions. Well, so why is it convenient to look at inner functions in these settings? Well, first of all, their level sets are spectra. So if you restrict your Dirac system on the interval from 0 to t, then the level sets of the inner function theta of tz give you various spectra of that system with various boundary conditions. Now, for people familiar with the Clark theory, this is not a surprise. The spectral measures can be recovered from theta using this Clark formula. Some additional properties. So our inner function, our meromorphic inner function theta of tz has that singular factor, the exponential factor, if and only if the interval from 0 to t was ending with the interval on which the potential was 0. So if the potential is 0 from t minus a to t, then we will have this exponential with frequency a in the factorization of theta. And that's the only way you can obtain that exponential part in that factorization. So normally theta is going to be just a Blaschke product. Well, and so, for instance, the poles of theta, which are at the points symmetric to the zeros of theta, they have physical meaning. So theta blows up at those points because they are resonances of the system. And by the way, one quick example of why it may be more convenient to consider inner functions than Hermite-Biehler functions, or M functions that they usually consider in such settings. So, for instance, if your problem is to recover the spectral measure from the set of resonances of the system, how do you do it using the inner function? Well, the points symmetric to the resonances, the complex conjugate points, they will give you the zeros of your Blaschke product. It's the standard operation to write a Blaschke product for the given collection of zeros. And then using this formula from your Blaschke product theta, you recover the spectral measure. So it's really a two-step standard operation. But if you are given, instead of a Blaschke product, the function E or the M function, if you need to recover the Cauchy integral from its zeros, that's you need one more step in this operation. All right, so now let's notice that this system of Dirac inner functions satisfies its own interesting differential equation. So the fact that those thetas were constructed using solutions to the Dirac system implies that thetas themselves satisfy the following Ricatti equation for each fixed spectral parameter z. So f is still the same function from our original Dirac system. The real function, which we, for this talk, assume to be NL2 on the half-life. So the Dirichlet condition for the Neumann condition for the initial Dirac system corresponds to the initial condition theta equals to 1, and the Dirichlet condition corresponds to the condition theta equals to -1 for this Ricatti equation. Now, I think that this Ricatti equation is interesting in its own right. So for us here, it will allow us to follow the dynamics of the resonances of the Dirac system. But I think it is interesting to study what happens to this equation with other initial conditions and so on. Let me say a few words about that. So if you start with any initial condition, where G, let's say first is any analytic function in the upper half plane, then all solutions of this equation will remain analytic in the upper half plane. Moreover, if you start with an inner initial condition, then all solutions will stay inner. And this is fun to see from this equation why this inner property will hold. And here is a quick illustration to this property. So in the left-hand side, we have the rate of change of the value of theta. And we are considering this equation now on the real line to see if the function will stay unimodular on the real line. And now what do we have on the right-hand side? The first term is orthogonal to the value of theta because x is real and then we multiply by I. Notice that the second term is also orthogonal to the value of theta, and here is a quick illustration to show it. So what we have here in parentheses, 1 minus theta squared is this vector, and it's orthogonal to theta. And f is real, so it stays orthogonal to theta. So the whole right-hand side stays orthogonal to theta. So the direction of change of theta is orthogonal to the value of theta at every point x, which means that it will stay unimodular if it was, if the initial condition was inner. So one of my next goals is to study how the zeros of theta behave for inner functions satisfying this equation with a general inner or even non-inner initial condition. Well, so on this slide, I wanted to show you how these inner functions are related to those A and B functions. And this is mostly for those people who are used to the notations for the nonlinear Fourier transform used in the notes by Tao and Thiele and other papers. So of course they're all related and they can be recalculated one through another. And I'm running a little bit out of time, so I'll skip this slide. All right, so from the Ricatti equation, we obtain the following important formula. So resonances of the system are the poles of the Dirac inner functions, and zeros of those inner functions are at the complex conjugate points. And so here, if you want to study the behavior of the resonances as t increases from 0 to infinity, we can instead study the behavior of zeros. It's the same thing. And here's the formula for the velocity of a zero of a Dirac inner function. And the velocity at each moment t is given by this simple formula. So this will help us a lot in the future. And now we start proving that extension of Correlation's theorem to the nonlinear case. And for that, first we will need two universality type statements. And the first statement is the following one. So we will eventually try to prove that resonances cannot approach real points on the real line as t tends to infinity, except possibly for the zero set of points on the real line. So let's choose a point on the real line and denote by by q of s c over t, the box centered at that point s on the real line of the size c over t. So the box will be shrinking with time. And let's denote by t naught as c the set of all t for which this box contains at least one zero of theta, at least one resonance at the moment t. So this is the set of bad moments in time at which this box contains at least one resonance. And the quick lemma, which reminds you of some universality type results. It says that for almost every s, if you tend t to infinity along that set of moments in time for which the box contains a resonance, your function will resemble more and more this very elementary inner function with zeros along an arithmetical progression. So along with your zero that is contained in the box, there will be a whole bunch of zeros on the same horizontal line. So the moral of this lemma is that if for those moments when there is at least one zero in the box, our function takes the simple form asymptotically in this sense. This could be also formulated in terms of the function e instead of theta, and for e we would have to say that e resembles the sign more and more. Well, this sign actually with zeros in the lower half plane. All right, what happens if there is no zero in the box? If there is no zero in the box, and this lemma I'll formulate in terms of e for a change. So if there is no zero in the box, then e in that box resembles more and more the exponential function, the zero-free exponential function. Also in this universality type statement in the sense of universality. So in both cases, when there is a zero and there's no zero, for almost every s in this shrinking box, our functions tend to something very manageable. Now, especially from the first lemma, we can almost exactly calculate the velocity of our zeros, because for this function, it's easy to find the derivative at the zero and use our formula for the velocity to find the velocity of the zero. And since theta is very close to this function, the velocities of its zeros must be close to this value. And now in main parts of the proof, so you want to show that the points on the real line are not approached by resonances except on a set of measure zero. First, you show that the set of all s for which this box contains a resonance for all sufficiently large t has measure zero. And this is relatively easy. You obtain a contradiction with Parseval's identity, because if there is a resonance in the box, then near this point, your function must oscillate. And the frequency of those oscillations must increase in time So there is no way to obey Parseval's inequality, because the functions with two different frequencies, they are very different in L2 norm. So it's not difficult to show that the resonance cannot stay in this box forever from some point on, except for S from a set of measure 0. So what remains to show? It remains to show that the resonance cannot get in and out of the box infinitely many times. So, but here we'll try to obtain a contradiction in the following way. If the resonance has to get in and out of the box, any box of any fixed size Q with any fixed C here, then it has to cross the space between the box of size 3C and the box of size C infinitely many times. And we will try to show that to cross the space back and forth infinitely many times, it will have to use too much of the L2 norm of the potential. Now, surprisingly, here, the proof splits into two different proofs, because if you follow the motion of the resonance, and now let's blow up our box multiplied by T, and let's denote by epsilon1 and epsilon2 the horizontal and vertical parts of the displacement of the resonance. So it turns out that you need two different estimates for the case when epsilon1 is about the same as epsilon2, and for the case when epsilon1 is much smaller than epsilon2. In the first case, when they are comparable, you use the nonlinear Parseval identity, and you see that you get this estimate, and unfortunately, there is a big disappointment, well, at least it was for me, when I saw that this inequality depends on epsilon1 linearly, but on epsilon2 only quadratically. So this method cannot finish the proof because of the square here. And so in the case when the resonance moves almost vertically towards S, I needed a completely different estimate. Just 1 second. And surprisingly, in this case, the main ingredient was the classical linear Parseval identity. So for the horizontal intervals, it was the nonlinear Parseval, and for vertical linear Parseval. But in both cases, you can prove that the displacement requires too much of the norm of F, and eventually prove that the resonance cannot approach the real line except at the zero set of points, and eventually use our second universality result for the case when there is no resonance to show that the absolute value of that Hermite-Biehler function E tends to a finite limit. W here is the density of the spectral measure of the system. I should have said it when we formulated that universality result. And eventually, after you prove that there are no resonances in the box for almost every S, you quickly finish the proof, because it implies that our F curly hat, our nonlinear Fourier transform, tends to this limit where all the functions involved also have a limit, and so and then you're done after that. So that is all. And so since this is the last talk in my mini course, I would like to thank the organizers one more time, not just for my lectures or this week, but for the whole program. And we truly appreciate what you're doing, guys. Thank you.
Thank you, Alex, and thank you for the wonderful talk. So let's thank Alex. And questions, comments, suggestions? the usual request to share your slides.
Right, sure. Yeah.
Thank you. Well, if there are no more questions.
Alex,
Oh,
I
there
have-
is a question. Javad.
Alex, I wasn't aware of the Michael Lassie's proof of the Pointwise convergence. Is this in a, recent paper, or you have a reference?
Not immediately, but I think you can Google it. So there's a proof by Lacey and Thiele, and there is a rendition of this proof by Michael.
Okay.
Just him. I think he wrote it when he was at the Schrödinger Institute, so it was a preprint, but it may be published now. So there are several written versions of that proof.
Okay, sure.
Yeah.
Maybe.
If
Thank
you cannot find it, email me and I'll
Sure.
look. Mhm.
I can ask Michael too. Thank you.
Yeah. Mhm.
More questions? Yes.
Can I ask a question? Yeah. You gave a lot of properties of this transform. Do we have also, for example, the Hermite-Biehler theorem?
A Hermite-Biehler theorem, I believe so, yes. Yes. So just 1 second, let me think. It's a good question. There are some Hermite-Biehler theorems floating around in this in this area. For instance, if you recall my last lecture, we defined the so-called Weil-Titchmarsh transform, which is the analog, or also an analog of the Fourier transform, but it's a linear analog. For the Weil-Titchmarsh transform, of course, there is a Hermite-Biehler theorem. The images of L2 of H on a finite interval will be a space, a de-branch space of functions of exponential type, T, and so on and so forth. For this nonlinear version that we are considering today, there must be some, but I don't really know it. And as you can see, I think that those functions A, B, A sharp, B sharp will still be of exponential type for a fixed T. Plus there is this nonlinear Parseval identity. So I guess you can define the nonlinear Hermite-Biehler space as functions of exponential type, satisfying this with this nonlinear norm from the Parseval's identity being finite on the real line. I haven't seen it discussed much, so I'm improvising here, but probably that would be an analog. But it's a good question. Yeah.
Thank you.
Thank you. And I think we should proceed with the next talk. Sorry, so probably the other question should be asked offline. So let's thank Alex again for this wonderful lecture and for the whole mini course. Thank you. And